welcome you all to the first session of short-term course and faculty development program on AI/ML-based controller design and deployment on real-time platforms conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. The speaker of the present session is Dr. Kuntal Mondal, Research and Development Engineer, IDIADA Automotive Technology, Spain. I take the opportunity to introduce Dr. Kuntal Mondal to you all. Dr. Kuntal Mondal, member IEEE IFSC, received the Bachelor of Engineering degree from the Jalpaiguri Government Engineering College, University of North Bengal, Siliguri, West Bengal, India in 2003. The Master of Control System Engineering degree from Jadavpur University, Kolkata in India in 2006. And the PhD degree from the Indian Institute of Technology, Kharagpur, West Bengal, India in 2013, all in electrical engineering. He was a postdoctoral researcher at the Indian Institute of Science, Education and Research, Kolkata, Mohanpur, West Bengal, India, and King Abdulaziz University, Jeddah, Saudi Arabia, from June 2012 to January 2017. He was an assistant professor with the Department of Electrical and Electronics Engineering, National Institute of Technology, Sikkim, India, from February 2017 to August 2022. He worked as Marie Curie Co-Fund Fellow with the Group D Automatica I Electronica Industrial GAEI and the Department Ingenieria D Ingenieria Electrica Automatica DAAA Universitat Rovira I Virgili, Tarragona, Spain, from September 2022 to August 2025. He currently works as Research and Development Engineer at IDIADA Automotive Technologies, Santa Oliva, Tarragona, Spain. His research interests include nonlinear control and dynamics of interconnected power electronic circuits, electric vehicles, chargers, and microgrids. With this brief introduction, I request Dr. Kuntal Mondal sir to address the participants. Over to you, sir.
Thank you very much for your nice introduction. And I want to thank the organizer for inviting me on this 5 days workshop on AIML based controller design uh, and deployment on real time platform. Can I ask one thing? I don't know why there is a sound behind. Is it audible to all?
No, sir. Sir, you are not audible.
Am I audible now?
Yes, sir. Yes.
Yes, sir, you are audible, sir.
Okay. Let me share my slide. screen window. Is it visible?
Yes, sir.
Yes, it is visible, sir.
Is it really? Okay, wait. Uh, Give me one moment. I really don't know what's happening. Can you see the screen? What's happening? I really don't know.
Yes, yes, sir. Yes, sir.
Screen is visible, sir. So,
I am continuously getting one sound and which is very irritating. I don't know why.
okay.
Now there is no sound. Yes.
Yes.
What? Again it started. What is this? I don't know really. Okay. Let me. Can you see the slide?
Yes, sir. Slide is visible, sir.
Yes,
And
sir.
full screen also.
Okay. Wait. Uh, Something is happening. I don't know. Uh, there is a sound like someone is calling, but uh, Miss, whenever I join, it started from that time. I don't know. Is it my problem or
Sir,
because
okay, sir. Is it possible
Dr.
to,
Mon?
sir? Can you rejoin, sir?
Okay.
So
Let
I
me try.
think I leave the meeting and rejoin, sir. I think maybe.
Sir, he might have connected from two systems, maybe.
Okay,
So the echo sound will come.
maybe.
He need to mute one system actually if he's getting
Okay,
the voice again.
okay.
Audible?
Yes, sir. Yes, sir.
Sir,
You're
you're
audible.
not.
Okay, okay. Thank you very much. I think okay. I think Arnav sent me two emails. So in another email was working. Okay. Thank you very much.
Okay.
Okay. So okay. The topic of my talk is different MPPT techniques for PV fed DC-DC converters. I will discuss about switched model, and I will also show the different experimental validation of different topology and techniques. So I am right now working at IDIADA Automotive Technology, uh, Tarragona, Spain, and the plan of the talk is as follows. First, I will talk about switching converters in PV applications where maximum power point tracking control or algorithm will be discussed. Then uh, classical control techniques using MPPT will be explained. Mainly two different types of this classical control. One is voltage mode control, another one is current mode control. Then sliding mode control using MPPT, voltage based as well as current based. And after discussing or doing a comparative analysis, uh, I'll talk about some instabilities due to parameter variations of the MPPT control as well as the environmental change like irradiance, temperature, and it will be explained through a simple peak current mode control where we will first see that subharmonic oscillation comes, and then with a proposed method it will be eliminated under environmental changes, and then with this proposed controller we'll be seeing the performance of a PV fed DC-DC converters. Many test cases will be discussed, and finally I'll conclude my talk. So in the general context, we can consider that PV panel, which is normally giving us a single panel, 36 volt to 40 volt, and to increase the voltage or current level, we have to connect it in series or in parallel, and this power will not be directly useful. So we need switching power converter for efficiency purpose, so that we can change the voltage level, current level, as well as the type of the DC uh, coming from the PV generator, so that it will be given to the home or directly to the DC load or AC load. So if we want to use this power to the AC load, again we have to convert that by inverter as shown here, and then we can use at it as it is. So to make it uh, independent, because as we know that at night there is no PV source, to make it independent irrespective of the grid, we need a battery. When at the daytime the battery will be charged, and at the night time the battery will be given to the home load, and in home there can be DC load or AC load. So when it is connected to the grid, or the home is also getting power from grid, then we have two sources. But even without grid, it can be worked as this, and it is called a microgrid. So in today's presentation, I will talk only about different MPPT technique and this DC-DC power conversion stage. I'll not talk about inverter, even battery. We can use this for the battery charging application, but in general, I'll be talking about the different MPPT control techniques for the DC-DC converter only. Now, now PV curve from the photovoltaic, we know that this is non-linear, or we can say it is piecewise linear. So in voltage current curve, it is like this. And if we draw it in voltage power, it will be giving me this curve. And this curve, we can see that there is a point when the power is maximum. So whenever we are using the photovoltaic, our main aim is to extract maximum power at all time. So this maximum power will change with irradiance as well as temperature. But a particular irradiance and temperature, there will be a unique operating point. And this unique operating point is denoted by maximum power point. And as I mentioned, this point will change with temperature as well as irradiance level. So we need a maximum power point tracking control. And to extract this, we are going to use DC-DC converter where using control of the switch or in terms of duty ratio, this maximum power will be extracted irrespective of the environmental changes like irradiance and temperature. And this load can be a resistive load, a current load, or a voltage load like battery. And as we can understand, this DC-DC converter is made by switch, inductor, capacitor. So this resistive load is working as a damping there. So instead of resistive load, if I use current load, it will be difficult to control. So in this talk, I will be considering all types of loads like constant voltage or battery load or resistive load or current load, and we will control with different techniques. So the main goal is to extract maximum power with the help of DC-DC converter by controlling the switch of the converter. Now, this is already known that in the maximum power point tracking control with DC for the DC-DC converter, we can do it in a different way. For example, in open loop, we can directly set D through PWM to control the switch. So in MPPT, two variables will be sensed and the maximum power will be calculated, and it will be given in terms of duty ratio to make the switch on and off for power conversion. And we can also use or regulate the PV voltage. For example, in this case, this MPPT algorithm will give us the voltage reference, and in the control, this voltage reference will be compared with the actual PV voltage, and then accordingly we can use PI controller to make the error zero and then control the switch. Similarly, we can use MPPT algorithm which will give us the current reference, and that current reference will be compared with IPV, that uh, PV current in the controller, and it can be a peak current mode control, and through PWM it will control the switch. So there are three possibilities by which we can control the input side. The main goal is to uh, extract maximum power, because as you have seen earlier in the graph, when there is a single point of PMM maximum power point, so when this will be set, automatically will reach to the maximum power point. And now, uh, among many MPPT control algorithm based on say intelligent based control, uh, particle swarm optimization, Partab and observe is the simplest one in terms of implementation as well as cost effectiveness. So in the whole talk, we'll be talking about Partab and observe for the MPPT, for as it is very simple in implementation as well as cost. And here we can see that in Partab and observe, we will Partab based on it is voltage mode or current mode. We'll Partab the voltage. We'll first mm, sense the PV voltage and PV current, and then calculate the power. And next step, we will again do that. If we find the previous power is less than the next one, then we will move forward like this, right? So when we'll reach there, in the next step, we'll be in this side. So after reaching this MPP, it will be this MPPT, that is the nature of the MPPT algorithm. It will oscillate around this maximum power point. So our main goal is to keep this oscillation as small as possible. For that, we can take small step size. But if we take small step size, it will take longer time to reach there. So for that, we can use adaptive control, so that the step change will be taken based on the situation where we are. So in all different control, this MPPT algorithm will track or extract the maximum power from the PV panel, and voltage mode and current mode control will be used uh, to regulate the maximum power point. Now, in this MPPT, Partab and observe, there are mainly two important parameters. One is MPPT frequency and MPPT perturbation. If it is voltage mode control, then this perturbation will be on voltage. And if it is current mode control, the perturbation will be on the current. The MPPT frequency, sampling frequency, is much smaller than the original PWM frequency. And we will see little later that there is a trade-off between this MPPT frequency and the DC-DC converter frequency. If it is these two parameters are not chosen uh, intelligently, then there will be interaction, and so that the normal behavior will be destroyed or disrupted. Now, using topology, let's see. Uh, let's choose that which control and which topology we are going to use. This diagram is showing a boost converter, and outside of the or output of the PV is connected to a capacitor to stabilize this voltage, and this is a duty cycle control. Similarly, this one is again a boost converter, and again at the output of the PV source, a capacitor is connected, and MPPT control has been used to set the reference, and then the PV voltage is compared with this and with suitable compensator. It can be PI compensator, it can be type 2 compensator, type 3 compensator. We are generating control voltage and comparing it with the ramp, so it will control the switch. In this case, we have used say resistance. In this case, we have used current load. This is the topology of SEPIC, which is giving me, as you know, that uh, boost converter will con the conversion will be lower voltage to a higher voltage, and in the SEPIC it can be buck or boost type, but it is different from buck boost because it is giving you uh, non-inverting output. So this will be very useful for battery charging application, for example. So in this case, we can see that we have used uh, current mode control, and the MPPT is giving me the uh, current reference for the current mode control. And a compensation has been used because in peak current mode control, if the duty ratio is more than 0.5, then it will give subharmonic oscillation. And accordingly, we can adjust this slope compensation magnitude so that the system will be stable for all duty ratio irrespective of the environmental changes or load changes. Environmental changes means the change related to the PV like irradiance and temperature. Now we'll be talking about how to select MPPT frequency and what is the impact of this MPPT frequency on the performance of the overall system. To quantify that, uh, three different types of efficiency has been defined. One is utilization efficiency, which is nothing but PV output by maximum power, and conversion efficiency, which is the output at the load or power, output power at the load uh, with the PV power. And system efficiency is nothing but the multiplication of this utilization efficiency and conversion efficiency. So here we are interested to see the utilization efficiency to quantify the efficiency of the MPPT process. And we can see by keeping switching frequency fixed, if we change the MPPT control frequency, this utilization efficiency is decreasing. And in opposite way, by keeping MPPT control frequency fixed, if we increase the switching frequency, then this utilization frequency is increasing. So we have to choose it carefully because we know that uh, this is we are talking about the efficiency of the MPPT method, but we also know that if we increase the switching frequency of the system, then switching losses will be higher. So with the higher switching frequency, this conversion efficiency will be lower. So the system efficiency, which is the multiplication of these two, will be lower. So we have to choose it carefully, where we have to see the good efficiency as well as the good tracking of MPP. Now, with the voltage based PWM, which we discussed earlier, of a DC-DC converter, we can see the performance. For example, at startup, it is slowly reaching to the maximum power, and in the steady state, it is there. This is considered that it is at a particular irradiance and temperature level. Next, the classical control using MPPT, because in all cases we are using perturb and observe MPPT method. And here now we see this is different than earlier three. Why? Because here we are using two loop control. That means that the outer loop control, which is given by the perturb and observe MPPT, is giving me VMPP, which is nothing but the reference. And with that, I am comparing the PV voltage. And then it is going to a PI compensator, which is generating my reference current. And then this, excuse me, then this inductor current is comparing with this reference current, and through flip-flop, it is generating the uh, gate pulse to the switch. So in this case, we can expect that it will give me the higher speed compared to the voltage mode control. And now it is also experimental validation has been done on this at startup. This is the waveform of uh, IPV, VPV, and power. This is nothing but multiplication of these two. And at steady state, it is showing me three step. As I mentioned earlier, that the optimized MPPT will give us three steps always. If it is more than three level signal, then it is not optimized. But with the variation of the uh, environmental condition, we can see that there are 5 level, 7 level, other level of non-optimized MPPT. I am talking, these all are related to perturb and observe method. So next is classical control with MPPT. The voltage mode control and current mode control has been already shown. Now we are talking about current based sliding mode control, and in this case also in the sliding mode, this IREF is generated by perturb and observe, and the switching surface is defined the nothing but the error of this IL, and this is nothing but IREF, because uh, to match the unit, this is conductance sum gain multiplied by VMPT. So this is nothing but IREF, and through hysteresis comparator we can switch on and off the system, and constant current load is used here. So compared to the earlier cases, we know that sliding mode control is faster, but in this case Along with these two measurement, VP and IP, we need another measurement of IL. It is also true for current-based classical control using MPPT, because we need one extra current sensor. So the cost will be higher. And in this case also, startup and steady state has been shown. And as we mentioned, there are two important parameters, uh, MPPT, the frequency of MPPT, and the the perturbation of that MPPT. Compared to the earlier cases, now we see the frequency of MPPT has been increased. In this case, switching frequency is 50 kilohertz. Now we will be talking about high gain DC-DC boost converter, because as we have seen that a single standard PV panel uh, will give me only 36 to 40 volt, but if we want to connect it with the grid, which is say, or DC link, which is 380, then this bigger conversion is not possible by simple boost converter topology. And that is why we need high gain DC-DC boost converter. And in high gain DC-DC boost converter, there are many topologies like quadratic boost converter. We can also cascade two boost converters, but in that case, the efficiency will be lower because of the multiple stages. So, in this high gain DC-DC boost converter, our aim is to step up the voltage from 36 to directly 380 or 400, like conversion ratio more than 10 or around 10, which is never possible by simple boost converter topology. That is why a switched inductor multi-cell boost converter has been chosen, and this topology is a high gain topology. And here we have used uh, voltage based sliding mode control. That means we don't need one extra current sensor, and that is why this topology with this sliding mode control is very fast, and it is scalable also by adding more leg to or more inductor here. So in this case, the analysis has been done by considering all the inductors are equal. Even there is a 10% mismatch, the performance is not deteriorated as much. And load, resistive load and in current load both are considered. But if we remove this resistive load, then see the damping factor is reduced. That means from stability viewpoint, it is difficult to stabilize. But with this is the experimental circuit diagram. Here in the multi-cell, we have used four cell or four inductor, so that our required voltage 360 from 36 to 40 can be achieved. And this is the flow chart of the control technique, and the sliding variable is just nothing but the error between the PV voltage and the generated reference by part of an observed MPPT. And if we see it, we can see that these are the parameter values. And now if MPPT has been increased to 1 kilohertz, and the perturbation has been taken 0.1 volt. And here we can see that we are reaching around 360 from 36 or 40 volt. And this is the steady state behavior. One interesting thing I want to tell here, that is normally current based control is faster, but in this case, if we see, we have used voltage based SMC, and this is a single loop. Normally when we use uh, and it is single loop, and it is faster than the current based DC-DC boost converter, current based sliding mode or SMC boost converter. Now, this has been tested with the step change in irradiance as well as load change. And here only current load is considered, and then we can see after a step change, it is uh, showing stable behavior. But as you know that we are not controlling the output voltage, because all this control has been applied from the input side, and that's why after load change or irradiance change, the voltage level is changing. So if we compare all these different control techniques using MPPT, in the literature we can see that for different topologies, boost buck, boost sepic, when a current based controller has been used, maximum MPPT speed has been like 100 hertz, 10 hertz, something like this. Even in case of boost, uh, high gain boost converter, if we see, then also this speed of MPPT is very low. But in this case, without using current sensor, due to the thanks to the topology, uh, we are able to achieve the highest speed compared to the earlier MPPT speed reported in the literature. Among all these, we have compared current based SMC, this proposed voltage based SMC, as well as a simple voltage based PWM without SMC. We have seen we are changing the power level. This is actually to show the or quantify the performance of all these controllers. So we are changing power not in step but with a slope and going to the highest level, and then we can see that while changing this step, uh, different controllers are behaving differently. The main goal is to track always the reference power. If you are not able to track the reference power, we are losing that power. So now if we draw this plot in error in power, then we can see that the proposed voltage based SMC is showing, if you take the area, minimum power compared to the uh, other, say, current based SMC or voltage based PWM, it is showing better result, the proposed voltage based SMC. Now, after discussing all these different kinds of control technique where the Partavan observed MPPT is giving the reference for voltage mode control or current mode control or sliding mode control. Let's see uh, what will happen or what measures can be taken if due to say current mode control of PV fed DC-DC converter is showing subharmonic oscillation. And in subharmonic oscillation, analysis is simple in the sense that we can only analyze the inductor current dynamics to understand the stability. And this is a typical inductor current of say converter. In this case, we consider uh, boost converter from the topology, and in the input side we can connect DC source because it is irrespective. This result is irrespective of the PV or DC source. So if we use a PV, we will analyze that how it will affect the overall system stability. So in the continuous time domain, the dynamics is governed by a first order differential equation where U is the switching signal in the square waveform and M1, M2 is the upslope and downslope. In discrete time domain, we can model it like this, and there we can find out the duty cycle in the discrete time domain. And after linearization, we will be getting this important parameter lambda, where uh, the values of this lambda will decide the stability. And we can see without doing this mathematics even, if we do this task of how peak current mode control has been used, then we can see that more than 0 0.5 duty ratio, it will show subharmonic oscillation, which can lead to chaos and other undesirable behavior. So this can be studied by a standard study of nonlinear dynamics. Now, when this subharmonic oscillation will start from here, we can see that based on this value, because it is discrete time model, so the lambda value will be uh, within the unit circle, and from here we can see when it is going this d 0.5 more than 0.5, it is violating this stability condition, and it start subharmonic oscillation. Now, this analysis is shown in the big diagram. Like this is the current reference, constant current reference. When you are more than 0.5, the system will show subharmonic oscillation. Now, how to eliminate that? To this is the picture when your current reference is constant and you are applying duty ratio more than 0.5. To avoid that, there is a very standard procedure of adding slope compensation in the circuit like this or this. Both are same. So earlier our reference was constant. Now we are adding a compensating ramp with the same frequency of the system, and then we can see from the picture itself it is clear the duty ratio 0.5, it is stable, it is showing period 1 behavior. That means in each switching cycle or it is repeating with the switching frequency. Now, how to calculate this value? If we see what will be the amplitude of this uh, voltage, then we can see that this amplitude depends on the slope, and this slope depends on inductor. So to set this value, this is the expression, and if this inductor and this m naught parameter on which it depends, if those are changing, this Vm will also change. Right? But if you fix this Vm, then if this changes, then even over 0.5, it may not be stable. So the advantages of this slope compensation is that this is a very standard circuit implementation. Many commercial chips are available. It will eliminate the subharmonic oscillation. Very well known technique. What are the disadvantages? Disadvantages are that, as I told you, that value you have to make it fixed, but that value depends on input output voltage. That slope depends on input output voltage. If so, then if the input side voltage changes or outside load changes, then this value will also change, but nobody is there to change it. We are making it fixed. Even if inductance changes, that value will change. But if we make it constant, then with these changes, this will not uh, adapted, or it is not adaptive type, that it will change the value for the stability. That is why we are proposing a new technique where this Vm is not fixed, and with some mathematics we will find the name of this compensation. Earlier it was a linear compensation, the slope was linear. Now this compensation is nonlinear, and will show that it is piecewise quadratic. We are doing the slope compensation, but in this case it is not coming from external ramp signal. It is coming from within the system. What is the advantage? We really don't need external compensating ramp. So the frequency will be adjusted automatically, and the as it is taking from the inside value, so it will be also called self compensation technique. Now we will change this constant value.
Excuse me, sir. So we can't hear you actually. You have muted yourself. Sorry to interrupt.
No, I think Shari will. Okay, maybe some issues following his end. Sir, you are muted, sir.
Hello.
Yes, sir. Now you're audible.
But how long I was muted?
Just for, I think, just 2-3 minutes.
How is it possible? Okay. Anyway. Okay.
That slide 30, we have that slide 30, your discussion we have. Yes.
Okay.
Yes, from yes, sir.
Okay. So let us start from here. Okay. So we have seen there is a standard procedure of putting uh, external compensating RAM. So now instead of external compensating RAM, we will generate this signal from the internal variables, and this is the methodology of generating this variable. So we are integrating the error. The error is nothing but the reference coming from the MPPT and the current, and then it is resetting in every cycle. And by this method, let's see that how this looks. So if we do this, this is a constant, and if we use this mathematical expression, it can be done by resettable switch in the hardware also. Then earlier it was constant slope, but now we will see that it will be like this. So from this to this, we can see we have two pieces of quadratic signal for this and that. So if we use this proposed method, then it will take care of the input changes as well as output changes, as well as the uh, parameters inside which are related to the slope of that constant magnitude. So now this value is auto tuned. So we don't need any manual setting for all the environmental changes. We can do it from inside. And not only that, now the system is stable for all the duty cycle, uh, like conventional slope compensation scheme. And these are the graph of duty ratio. We can see that now this value will be between this and this. So there is no subharmonic oscillation at all. Now apply this technique on SEPIC. This graph, this current versus power and current versus voltage, it is, or VI curve, it is upside down because instead of voltage mode, I am using current mode. That is why it has been drawn in this way. So now we will do some tests to check that. Now see, test one, that start up with static weather conditions, and we can see that it is working fine. That means PV, this is the PV. So at the starting, it is slowly catching the MPPT. And the irradiance is 1000 watt per meter square. Now, wait, conventional, okay. Now, this is with conventional technique, and this is with piecewise quadratic technique. Both are stable at this point. Now we see that sudden change in the irradiance level. So we are changing the irradiance level from this to this to this. And now we see that with the conventional technique, we are getting this. Can you see that In this case, ripple is higher. And if we zoom it, we'll see already subharmonic oscillation started. Do not forget that here I have used the external compensating RAM, but with a fixed value. We can increase that to do that, but that means a manual setting is needed. But still, irrespective although we have used the slope compensation technique, we are still in the subharmonic oscillation due to the bad choice of this slope. Now, with PWQ at the same condition, we see that uh, there is no subharmonic oscillation. Test condition 3. Now, this is it initially looks non-practical. For example, I change the inductor value, right? Actually, when a system will be there due to drifting and an aging, the value can change. It will take long time, but if we see the effectiveness of the controller, then we can see that with the conventional one, if there is a sudden change in inductance value, because that inductance value is related to the slope, which is deciding the magnitude of the compensating ramp. It will show the subharmonic oscillation, but with this PWQ or piecewise quadratic method, there is no subharmonic oscillation. So, in conclusion, I can say that different uh, control technique using perturb and observe MPPT has been studied and is compared in terms of MPPT speed, and finally we have seen for high gain DC-DC boost converter, a single loop voltage based MPPT has been proposed, which can directly stepping up the voltage from 36 to 380. That means conversion ratio more than 10 using a switched inductor multi-cell boost converter, which will be suitable for grid connecting PV. And then we have also shown or proposed one current control technique using MPPT, which will eliminate subharmonic oscillation under any weather change or parameter change inside, and we really don't need to adjust the slope offline. It is adaptive. We can call it self-compensating RAM, which is the signal is coming within the system, and this piecewise quadratic compensation strategy extract a compensating signal directly from the error. So it doesn't need any external signal. Uh, so in that sense, it is less costly compared to the compensating external compensating RAM. Thank you. So if you have any question, I am ready to answer.
Hello, sir. This is Prashant
Yes.
here. Uh,
Yes.
Sir, in one of the slide, in the starting slide, you have
Okay,
mentioned
right.
a three level signal and two parameter.
Yeah.
So, what actually what is the meaning of three level signal? I could not understand.
Okay. Okay. This one, right?
Yes, sir.
Yes. Okay. So can you see here? So as it is perturb and observe, you cannot stay here. correct? So you have to take one step this side and that side. That means what I'm trying to say is that this is the optimized pattern observed, but there are, for example, you can also see 5 level this thing. That means the oscillating, how it is oscillating around that maximum power point. Because you are in pattern observe, if it is current based, then you are actually, this MPPT algorithm is changing this, right? Delta I. If it is
Yes.
voltage based, you are changing del V, right? Which I have
Yes, sir.
shown in almost all slides, right? So you are generating these references, right? And you are never here. You are never here. You are doing like this, correct?
Yes.
And that's why the optimum one is 3 level, right? Where, uh, for example, let me see if I can find. I think 5 level. Okay, let me see here if I get it. Okay, can you see this?
Yes,
Can
sir.
you see this? See, uh, this 3 level, correct? Let me see when it is not optimum, how much I can get. I have seen. I think there are 5 level also. Let me see this one. If you zoom it, you will. Okay, let's see this one. Mm, okay, I can see it. Can you see this zooming stuff? But let me show it clearly. Can you see it? Here it is not 3 level.
Yes, sir.
It is more than, and as it is not that, see, the undesirable behavior starts. It is not period one or desired behavior, what you wanted. So for different environmental condition, you can analyze this part separately, that under which parameter you are getting 3 level, under which parameter value, right? You are getting 5 level, because this is cycle level dynamics. If
Yes,
you
sir.
don't choose your numerical values correctly, you will find, oh, it all looks same, right? But it is not that all look same. Okay.
Thank you, sir.
Yeah.
Excuse me, sir.
Yes,
Am I audible?
yes, you are audible.
Okay. Sir, this is Rasheshri Pradhan from VSS Tibulla.
Okay.
Sir, I have one question. Sir, you have used current-based MPPT, na?
Yes.
Sir, sir, in conventionally, MPPTs are used usually voltage-based, I think. So, what is the benefit of it?
Okay. Keep it
Why you have
simple.
used
Uh,
current-based?
keep it simple. Forget about MPPT.
Mm-hmm.
Normally, voltage mode control, current mode control.
Yeah.
So current mode control is faster than voltage mode control. Agree?
Okay, sir.
Okay. So I am using the same concept, not I am using, all are using the same concept to make it faster. That's it.
But sir, in that the graph of the that solar system, that PV curve or IV curve, sir, usually we have different region, na? And I think whenever we are doing the current control, it will be in the unstable region, the stable region, unstable region, like this, na? So I think you will be in the unstable region.
Okay.
So if
So
current control.
okay, you are trying to say a partial shading, or if I am here, right?
No. In this curve, sir, in this curve, so we have near this ISC, that is the unstable. Usually that is the unstable region, na? So tends to unstable region, and near the VOC it is stable region. So that's why I think, I have that doubt. So that is usually tends to in on stability. That's why people are work to near the VOC point. They usually move for MP that especially for MPPT. I'm asking.
Okay. As per my knowledge, uh, for all step change, the MPPT algorithm will be stable or not. It depends on what I am using. Say, for example, I am using here part of an observe. There is incremental conductance method, right? But try to understand, I am using voltage based or current based where reference is coming from MPPT. So that is related to the MPPT algorithm. Got it? For example, part of an observe has one disadvantages, like if you are in this zone, sometimes if you go there, you will not come back, right? But the general rule is I am using here current based and voltage based. It has nothing to do with that MPPT algorithm. Are you getting my point? See,
Sir, okay.
all my structure. Okay, this is important part. See, this is important. MPPT is this, control is this. So when I am generating IREF, right, inside the control, if I am comparing it with IPV, then I can say it is current control, right? Similarly here, voltage control. Similarly here, there is another one, two loop control. Let me see it. Uh, oh my God. Where is two loop control? This. Oh, this is two loop control. Can you see? See, in all these cases, reference is generated by P part of an observe MPPT. If that MPPT algorithm has some problem, right, he cannot come back from certain position, then I cannot do anything. Okay.
Okay, sir.
Morning, sir. Am I audible?
Yes. Yes.
Sir, this is Reshma from MIT Manipal. I have a question. Basically, in your slides, most of the slides you have explained the converters, especially boost and SEPI converters. So why only these converters? Can we go for any other converters, or like on what basis do we select these converters when it is associated with PV?
Very good. Very good question. Okay. Uh, Normally, when we connect PV, we want a continuous current,
Okay.
right, from PV. So look at carefully. For example, if I want buck boost, right? Say I want higher voltage, lower voltage, then I can also use choke converter. But here I am not using choke converter because the input current is discontinuous. Okay. In case of SEPIC and boost, as there is one inductor at the input, so current is continuous, which will enhance the life of the PV cell, PV panel.
What about other converters like buck converters?
Buck converter, you see, input current is discontinuous. Buck boost converter, it is the output is not output is inverting, not non-inverting. Are you getting?
Yes, yes.
So these two cases you will find the uh, continuous current in the input side. I think, if I am not wrong, the high gain converter I have chosen, right? In this case also, the input side there is inductor. So the current is continuous. Yep.
Sir, if we use a ZVS boost converter, then will there be any difficulty or easier compared to using only a boost converter?
ZVS, I cannot remember the type of topology. If I see the topology, I can say what it is doing.
The same function as the boost, but
Are you
some
talking about
parameters we are getting.
quadratic boost converter, something like that?
Yes, sir. Zero voltage switching boost converters, ZVS boost converters. We have
Okay.
ZVS and ZCS converter. Similar concept is applied to a boost converter.
Okay. Understood. Okay. See, whatever here we are doing, in all cases, it is a hard switch. You know, hard switched and soft switch. For example, simple DC-DC converter, these are hard switched. So resonant converters where this zero voltage switching or zero current switchings are used. Those are soft switching converters, which has the characteristics of reducing switching loss drastically, right? So,
Yes, sir.
in my opinion, uh, that means in those cases, what they're doing, they are actually putting some resonant component, very small value LC to make the switching process soft, right? In my opinion,
Yes, sir.
that has nothing to do with this. Means, that is only useful for the switching process. So whatever we are using, we can still use that. If we always want the good feature like input continuous current, that is only the thing. Yeah.
Yes, sir. Thank you, sir.
Hello, good morning, sir. This is Deep Kamal. Am I audible?
Yes, clearly audible.
Sir, I have few questions. Like the high gain DC to DC converter you are using. So what's the gain value for that?
Here, okay. I can tell you the motivation behind using this.
Okay.
This gain value, what experimentally I am able to achieve is 11 or 12. 11 to not more than 12. That is true.
Okay.
There is one paper who proposed this, And this is interesting because this is the only one Huygens topology to the best of our knowledge where we can use voltage-based SMC which will perform better than current-based SMC, sliding mode control. That means after deriving, the derivation is such that you just use normally current-based controller are faster than voltage-based controller. Not only that, in all the topology, say all basic possible converters like buck, boost, buck boost, sepic, even take chook, right? We have checked or applied this method to all of them. This feature is not available, right?
Okay.
This is one of the things that this sliding mode voltage based, still fast single loop voltage based sliding mode control has been used here, only applicable for this topology, right?
Yes.
Because in that paper, we have analyzed all, in this paper, we have analyzed all the topology, possible topology. I didn't give it here, but there I found that that is there. But yes, one thing you may consider from other viewpoint. This is purely control viewpoint. That in this
Okay.
topology, it is possible. It is happening. Okay. Now you can consider that. See, the number of diodes. The number of diodes are. You may get better topology from efficiency viewpoint, like quadratic boost converter, right?
Hmm. Yes.
I think that efficiency will be more than this. But this work has been done completely from control viewpoint. That this is first time reported that it is fast single loop voltage based. That means you are actually saving cost of a current sensor. Still, actually, our claim was it is 10 times faster than the normal SMC.
Sir, another question is that like, have you seen any kind of like modern techniques like model predictive control such as for MPPT? Like, is it experimentally can be done? Is it possible?
Okay, good question. Right. Okay. Whenever, for example, during the publication procedure, a lot of reviewers are asked actually about to mention in our work because, as I mentioned from the beginning, that this is classical, all are mainly uh, voltage based and current based, but there are lot of literature based on intelligent based control, optimization based control, and sometimes a hybrid of that, right?
Yes. Yes.
So every time reviewers are asking and they're also claiming. I don't have much exposure on that, so that's why I can comment. But those reviewers are actually telling there are very better, maybe good control if you go for intelligent control or hybrid means uh, particle sum optimization with fuzzy logic, right? So
Yes, sir.
taking from intelligent control and from optimization technique, so they outperform all these maybe. But I don't have much exposure on that.
Okay, sir. Thank you. Thank you so much.
I think a lot of queries, a lot of question was there, and Sir has answered all the questions. So thank you, sir. And I think this is a very good
Sir,
session.
can I ask one question?
Yes,
Actually, I was not able to unmute
That's
that,
okay,
sir.
but it will be the last question. Okay. Actually, sir is giving answer last, I think, 20, more than 20 minutes. Okay. Okay, sir. Please take the last question. Okay.
Acha, thank you very much. One question I was asking that suppose it is a high gain converter, then you expect more voltage, suppose 380 volts something from the input voltage, like if the voltage gain is 10 and 38 to 380. Then we get a high voltage and less current. So if we there in the input side, the current will be more than because it is a boost converter. So input side current will be more. So is it possible for that PV source to supply this much amount of current to our converter?
what current you want? What current you
Current,
want? Tell me.
yeah, input current value means from the
You
PV
know,
source.
okay.
PV source.
You know that I am talking about only one panel, right? But you know that you can put it parallel, you can put it in series, right? There is a lot of research going on. So how to connect those things reliably so that you can increase the voltage and also based on your connection, how you are connecting, you can increase the current as well as voltage. So from panel, you have to go to module, right? And accordingly, you can do that. But here, what I did is that one single PV, and from there, uh, 360. Because this high gain DC boost converter is giving me 10 times conversion ratio. For example, if one PV panel is giving you 40 volt 10 ampere, then you can connect it in a way so that 10, for example, to make it 100 ampere. Are you getting?
Yes, sir. Yes, sir.
Yes. Yes. But yes, those connection is tricky. Means it is not like you have to check a hotspot and all these things.
Yes, sir. Thank you.
Hmm.
Okay, sir. It was very nice presentation. Okay, a lot
Thank you
of
very
things you
much
are
also.
able to understand. And I
Okay.
think the participants are also know a lot of things about that current mode control and current mode control based MPPT basically with the experimental results and a lot of things we have discussed. And I think it's really very good to us. Okay, so thank you, sir, for giving your valuable time and share your very important knowledge to us. Thank you, sir.
So, thank you for inviting me. Still in
Yes, sir.
Spain, there is night. Okay, in 1 hour it will be day. Okay.
So, can you share these slides for reference, like, if possible?
Yes,
Yes,
I'll
yes,
give
sir.
it
Really request.
to Ordno, and Ordno will distribute it because all these materials are available in public domain. But yes, I can understand uh, there is a problem of subscription of those papers. Yeah, that's a big problem. Yeah, but I'll share. I'll give it to you. Yeah. Okay. Okay. Thank you. Thank you very much for
Thank you,
inviting
sir.
me.
Thank you.
Thank you.
Yeah.
Welcome. So all the esteemed participants, please wait